completeness property, and he showed that in the class of metric spaces it's equivalent to complete metrizability by showing that the non-empty player has a winning strategy in the Choquet game on a domain representable space. Bennett and Lutzer proved a lot of things about domain representable spaces. One is that it's preserved under G delta subspaces. So the original question would be answered if domain representable implied subcompact. But Bill and I showed that there's an example of a domain representable space that isn't subcompact, so it's a strictly weaker property. This example is an extension of Deb's example of a space on which the non-empty player has a winning strategy in the Bonnick-Mazur game, but no stationary winning strategy. I have to mention games, I promised I would. So, okay, so we have right now two generalized notions of complete metrizability, subcompact and weaker domain representability. I think, let me look at my time. Let me skip to, sorry. I wanted to skip to something in between that I learned about this summer. So Chetan Vural presented a new completeness property defined from pair bases. So domain representable and subcompact have bases in them, right? I mean, the convergence is quantified in bases or index bases. A pair base is a different sort of object that acts sort of like a base in the following way. It's a collection of pairs of subsets of X, A, B, where the first coordinate A is open, and then A closures inside B, and it acts like a base in this way. If you give me a point and an open set containing it, you can find a pair in the pair base that sort of sits in between. X is in A, B is in U. And you can define a natural relation between the pairs. You say AB is less than CD if B is contained in C. And they say that a pair base is complete if you take a collection of pairs directed by this relation and its intersection is non-empty. Oh, pardon me, not its intersection. The intersection of either the first or second coordinates is non-empty. It's equivalent. This being non-empty is equivalent to that being non-empty. Okay, so they showed that a subcompact space will have a complete pair base, and it's straightforward. If you have a subcompact base, just take pairs from that base that satisfies closure of A is inside B. And then any directed collection of pairs will produce a regular open filter base from the A's in B, which is guaranteed to have non-empty intersection. So that's nice. It's very easy. Likewise, if you have a complete pair base, then you can build a sort of indexing, that domain representable indexing. How do you do that? Start with a complete pair base. Grab any base, Q, and it's going to index itself. For two members of that base, say that U is way below V if there's a pair in between. Then a collection that's directed in Q, they're a directed collection of indices, but they're also a directed collection of members of that base. They're going to have non-empty intersection because there's an intertwined collection of pairs, and the A's have non-empty intersection. So you have, having a complete pair base is sitting in between subcompact and domain representable. What's even more interesting is that they showed that check complete spaces have a complete pair base. In fact, they showed that having a complete pair base is hereditary to dense G delta subspaces. And that argument is written out here, but essentially what you're doing is you're starting with a complete pair base of an X, you're defining a natural one down here on Y, and you're making sure your pairs intertwine. I mean, you get to spread out the pairs in your pair base, sort of incorporating any kind of space that you want. And in this case, you've got a G delta to work with, so you do the same sort of spacing out with the UNs, and then you also incorporate the pair base spacing from the original space. So it works, and you get that check complete spaces have a complete pair base. Okay, so there's a couple possibilities here. Maybe this isn't a new property, and it coincides with subcompact, or it coincides with domain representability. Well, I skipped over the slide that talked about what the Choquet game is, but if you don't know what the game is, you have two players, they're selecting open sets, and they create a decreasing sequence of open sets. The player whose name is non-empty wants that intersection to be non-empty. That's all you really need to know. So if you have, what do I want to say? Oh, if a space has a complete pair base, then non-empty can win the Choquet game with a stationary winning strategy. So if empty plays an open set U with a point inside, non-empty is supposed to respond with an open set in between X and U. And what he does is he looks back up at the complete pair base and just makes sure that he squeezes a pair in between. You can do that because that's one of the pair base properties. And then non-empty is just going to respond with that A. So the sequence of plays is going to have non-empty intersection because the ordering on the pairs that he plays is a loose ordering. It's easy to satisfy that ordering is what I'm saying. So he can win with a stationary winning strategy. So we know then that having a complete pair base is strictly stronger than domain representability because in Bill and my example, the domain representable space, we showed it wasn't subcompact by arguing that non-empty didn't have a stationary winning strategy. So this cannot, domain representability can't imply having a complete pair base. So either this implies that, in which case the G delta problem, or well, the check complete implies subcompact problem is solved, or it's a new property. So the question I'd like to ask is if a space has a complete pair base, is it subcompact? Okay, so with 2 minutes left, I'll skip through a lot of other stuff and just put a couple other questions here. Topological games can quantify certain completeness properties. I've just touched on the relationship a little bit between those things. How much information non-empty can win with is an interesting question. So I mentioned stationary winning strategies. There are instances where non-empty can win with more information but not less information. And there are two questions that I've been looking at, if you know the terms. I want to know if non-empty has a coding winning strategy in the Choquet game. Does non-empty have a winning 2 tactic? In particular, I don't know if even in dev space, non-empty has a winning 2 tactic. In the Choquet game, I mean to say. I mean, he has a winning 2 tactic in the Banach-Mazur game, but what about the Choquet game? Cellular families are used to sort of do coding, even indirectly into tactics, and cellular families don't help at all with the Choquet game, so I think I put that up there. So I'm wondering about those two.
What is that coding winning strategy?
Coding winning strategy, non-empty player, or the player can see his opponent's previous move, certainly, and he can see his own previous move. So when he sees his own previous move, he can store a lot of information into that. And if in tactics, you can only see your opponent's moves, you have to indirectly code into their moves, which is harder. Okay, that's it then. Thanks.
Are there any questions?
So I think this was a slide, but it went too fast.
Sorry.
So suppose you have a subcompact space, and I give you another base unrelated to the one that you started.
I can't find a subbase that's subcompact.
No, I don't think.
Oh, but go ahead, go
I
ahead.
kind of expect that.
Okay.
Are you saying that, but you can get up the pair base then?
Wait, say it again? So
Okay.
I have a subcompact space. I start with any?
I start with the subcompact space, and then I give you another base for the space. Can you find a pair base whose members are from the new
The given base. I don't know if that's a yes or no question. I didn't put that though. I started with the subcompact base and got the pair base. But I don't know. Because, I mean, you get the pair base directly from the special subcompact base in that slide. I do know of an example of a space that has, that is subcompact and has a base of which no subbase is a subcompact base.
It's interesting that for the stronger Amsterdam properties, the results, we know that examples where you can't get what you want. I mean, start with a base compact space, or things can go wrong.
Yeah.
Arts and I had a big problem.
But in Amsterdam, you can get into.
Any other questions? Okay, well, let's thank the speaker once again. Time for a coffee break.